Hello, my name is Oliver Maiß and I lead the Research and Development Department here at ECOROLL. Today, I would like to tell you something about the solid rolling of curved arches and radii and what you need to consider in this process. Curved arches and radii are important elements of mechanical engineering. They are always used where shaft steps occur and where one diameter follows another. This is exactly where the highest stresses occur under load. Here we have stress peaks that cause the material to yield at this point. This means that a shaft will always break at the transition of the radii. We have simulated this here. You can see it in a simulated wheel carrier where we have introduced a radius. We are applying a defined force to this wheel carrier. And what we naturally see is that right at the top, where the highest tensile stresses are, there is the greatest load. A component will eventually crack under dynamic load at this point. In our studies, we learn how to handle this. We should design the transitions of the radii as smoothly as possible, meaning we should use the largest radii possible to reduce the notch effect. If that doesn't work, we could use other materials, which are naturally more expensive and more difficult to obtain and process. But all of this leads to an improvement in lifespan, but it also always results in a change in the design and a change in the component. In a previous project, we investigated how much we can change the lifespan of a wheel carrier by altering the geometry, the material, or the edge zone. By altering the edge zone through simple solid rolling, we were able to increase the lifespan by a factor of 5. This is a tremendous increase compared to the other two strategies, and it ensures that we have no changes to the component. Through solid rolling, we introduce compressive residual stresses into the edge zone. These compressive residual stresses have a crack-inhibiting effect. This means that cracks are prevented from forming and spreading because they are compressed by the internal stresses within the structure. This means that crack growth progresses more slowly, and my component will simply last longer under the load. To introduce the compressive residual stresses, we use the process of solid rolling. In solid rolling, a rolling wheel or rolling body is pressed into a surface with a defined rolling force. It then rolls over the surface by applying a feed speed. That means we basically have 3 parameters. We have the roll geometry, which determines the contact area. Then we have the rolling force, and we have the feed. The geometry and also the feed are actually well controllable through the process. The feed rate can be entered in the NC program, and it is fixed. If nothing is changed in the program, this feed rate will remain in effect. The roll geometry is also defined. All manufacturers, including us and all others, naturally check our rolling rolls for the corresponding geometry. This means that the rolling roll and the contact geometry are also very rigid parameters that are generally not changeable by the process. The third parameter, the rolling force, on the other hand, can change during the process. We can make errors when measuring the tools. We can make errors during the pre-processing. We can have temperature adjustments. We can simply define the rolling force incorrectly. We can set a wrong programming for the delivery. There are various parameters that we can change to alter the rolling force. However, we do not see it in the process results. The rolling force is so crucial that it is truly the only parameter that can significantly control the introduction of compressive residual stresses. So, if we can define the rolling force and control the rolling force, then we are also able to control the introduction of compressive residual stresses. That is why we have developed our EcoSense technology, for example. A digital measuring gauge that is integrated into our tools, which monitors every single processing step, every single rolling. We can document securely. For processing curved arches and radii, we use single roll mechanical tools. In this type of tool, a rolling roll is held axially and radially, and it can then be precisely controlled over the surface. This means that through my NC code, I can define the rolling force at each individual point. I can change my feed rate and thereby influence the rolling force. Why does it work? Because these tools are equipped with leaf springs. I have the rolling roller installed at an angle of 45 degrees. This rolling roll at 45 degrees allows me to process a wrapping angle of 90 degrees. There are leaf spring packages positioned at 90 degrees to the rolling cylinder. This orientation allows for a deflection of the rolling cylinder when I bring my tool into collision with my component. That means I essentially position my roll. I drive into the component and simultaneously guide the leaf springs out. This deflection of the leaf springs then defines the rolling force. This is also what we measure with our measuring gauges. Both the analog and digital measuring gauges actually only measure the deflection of the leaf spring and then transfer this either analog or digitally into a force value. This force value is of course calibrated. It is predetermined, but we have a spring characteristic that correlates this spring travel with the rolling force. If we want to control the rolling force in the process, we must of course consider the angle of force application. The whole thing is of course somewhat exaggerated at this point. The rolling force is not that sensitive. I just need to ensure that it has the right value at the right place. So now, when I define my rolling force for a process, and I have simulated the whole thing, I have tested it on cylindrical components. Then of course, I have to try to achieve the required rolling force in the curved arch. And for that, I need to know that this rolling force changes depending on what my angle of attack is. Because of course, this rolling roller is positioned at the appropriate angle to the springs, and the angle of force application is then designed accordingly. I would like to sincerely thank you for your attention. If you have any questions or comments, please feel free to contact me or my colleagues at ECOROLL AG.